So now we have talked about RCNN and we talked about fast RCNN. So just a quick recap of what each of these mean. Well, RCNN, what it basically does is, first it starts the image with selective search, and after selective search 2000 region proposals are given out. Selective search is basically a segmentation technique, and using those segmentation we find the corresponding bounding boxes. So these 2000 region proposals are first warped to form a 224 image. Once you have these region proposals, each region proposal is passed one by one through VGG, through backbone VGG actually. So through backbone VGG is basically VGG without the bottleneck features. Once you have that, what it does is it basically gives out feature maps. Once you have these feature maps, they are divided into two parts. One, you have two fully connected layers, I suppose, and fully connected layers here, and this is used as a boundary box regressor. So this is a regression model here, and here you have SVM scores, right? So SVM score basically gives out what is the confidence of the object belonging to the particular SVM, okay? And bounding box regressors are basically used to give better values of the regions that have been proposed by selective search. Problem with RCNN, the one problem with RCNN is that each region has to pass one by one through VGG, which is very computationally expensive, and hence it uses 46 seconds, which is a lot of time. So we come across fast RCNN. So in fast RCNN we come across something known as region proposals projection into the feature map, and we come across region of interest. Okay, region of interest pooling, sorry. So how does all of this work? So you have selective search, obviously. In selective search you pass the image and you get the region proposals, right? And here what you do, you pass the image into a VGG network, again backbone VGG. You get the feature maps. Once you have the feature maps and the region proposals, what you do is an ROI pooling, region of interest pooling, and region of interest, once you have that, you project the values, and once the values are projected, now it passes through an ROI pooling layer to get fixed features, so features of fixed size. And once you have that, you have fully connected layers, two fully connected layers, and then you have what is known as two different sibling kind of models. So one, here you have a softmax model, this is used for classification, and here you have is a regression model. And so the loss is basically log loss, which comes from classification, plus the regression loss, L1 smooth regression. Okay, so this was the whole thing about fast RCNN. Now what we will be talking about is faster RCNN. So it is all fine, fast RCNN is not bad, everything there is fine. Fast RCNN takes about 2 seconds to compute the test time. This again is a big time. I mean, if you think about numbers, it is a big time, because you cannot wait for 2 seconds for a car to move forward or backward or take any direction, right? So we have faster RCNN. So what the researchers did, they actually went through the whole model and found out which part or which algorithm took the most time. So what they found out is selective search took the most time, because selective search uses CPU. So it uses CPU to actually find the values, which could actually be done way faster if we were using just a GPU. But selective search is a traditional algorithm, hence this had to be removed. So what they came up with is faster RCNN. So in faster RCNN, everything remains just the same, except instead of selective search, they have a region proposal network. So we have region proposals, right? Region proposals were through the selective search. Selective search gave us region proposals. Now we will be doing is region proposal network. So there will be a network that will do this task, and this network will be faster than selective search. So that is the whole point of this whole thing. Except that if you see faster RCNN, you have an image, it is passing through convolution layer, same, you get the feature maps, you have the region proposal, this gives out regions. Once you have these regions, you are doing an ROI pooling on the feature map, see projected region proposals, then this is followed by an ROI pooling to get fixed size features. Once you have that fixed size features, you have this two fully connected layers, and then you have a multi-class classification and a bounding box regression model, right? So this is basically softmax, and here you have whatever the loss be, regression loss, right? So everything else remains the same. The structure with faster RCNN and the structure with faster RCNN and fast RCNN is very similar. So there is not a lot of difference there. So the main thing with faster RCNN is basically that you have a RPN network. So RPN is basically region proposal network. So let us understand this RPN network, alright. So talk about RPN network. So first of all, let's come here. So one of the things that you might have seen is, see, in RPN you do not have an input image, right? So there is no input image. So what is the input here in RPN? RPN, the input is feature maps. So the other thing that they took care of is, see, when you were doing fast RCNN, so in fast RCNN, what was happening was you had the input image, this was passing through VGG, but at the same time this image was also passing through selective search to get the regions. So instead of having two time input into the image input two times, it just made sure that the input is the image is input only one time, and you have the feature maps. Now these feature maps will be passing through an RPN. Now talk about RPN architecture, alright. So what is an RPN architecture? Before that, let me introduce to something known as anchors. So this concept was introduced in the paper itself, and what they did was basically, let us just not make sure about this image for now, okay, let us just remove that and let us look in this image. So what they have done is basically, see, you have an image, and for every pixel, every window or every pixel in that image, the center point is known as an anchor of the, okay, so you have that center point as the anchor. So that is basically what is known as anchor. Now I am going to explain why this is important. Let us first understand about the basic RPN structure. So you have the RPN, right? So it inputs feature maps that you got from the VGG network or any convolution network, whatever, and then these feature maps are passed through a 3x3 convolution network, 512 filters and one padding. Now I'll say why this is all happening. After this happens, it gets divided into two different regions. So you have a 1x1 convolution here and another 1x1 convolution here, alright. And this convolution basically is used to give out 2k values. So 2k values means this is a classifier model here, and this classifies whether your anchor, the output that has been, is basically a background or not a background. So till now what we were doing is, when we were going for classification here, right? So when we were going for classification here, we had k+1 classes where one stood for the background part. But here in RPN itself does the task of saying whether this is a background or not. So what is happening is, you have anchors, and each anchor, so you have a 3x3 sliding window, okay. So what happens in RPN is, you have a 3x3 sliding window, and this sliding window slides from each and every part, okay. So for each sliding window there is a center. So this center is the anchor center, alright. Now this center is responsible to give out 9 anchor boxes. So for every 3x3 window, you have to give out 9 anchor boxes, alright. These anchor boxes are of different sizes and ratios or scales. So one box can be, let's say, like this. the other you can have like this. At the same time you can have something like this and like this. So whatever, so all of these boxes, their center will be here, but the boxes size will be different as well as the ratios are different. Alright, so here let's suppose this is a 4:1 ratio, this might be a 2:1 ratio or whatever. Now you get the point. So each anchor is responsible to give out 9 anchor boxes. So now you can see here, see, this is your sliding window. So this is a 3x3 sliding window. The center is the center of K anchors. So while training, what they have done is they have used 9 anchors here. So now these anchors, now you can see the anchor sizes are different, right? Sizes as well as the ratios are different, because this is so that it can accumulate the shape of an object. So despite any shape of the object, anchor size must be perfect enough to fit the object, right? So let's say if I have a cat here, right? So it is like this. So in that case, this anchor is not good enough, maybe this anchor is good enough, right? You are getting my point. So that is why we have anchors of different shapes, sizes as well as different ratios. So now once you have that, they are passed through, the feature maps are passed through 3x3 convolution, and it has 512 filters. Once that is done, now what will happen is it will pass through a classifier. So once you have that, it will be passing through classifier, 1x1 classifier, and here also you have 1x1. This 1x1 will be basically followed by a regressor. So this is basically a regressor. It will give out 4k outputs. Okay, so here instead of giving out outputs which are the coordinates of the boxes, what they will do here is they will give out something known as delta x center, delta y center, and delta width and delta height. So what that means is, see, you are already generating anchor boxes here. Anchor boxes are already being generated. You have given out the ratios. So the ratio might be 2:1, 1:1, 1:0.5, right? You have these ratios and these ratios have been given out. Okay, so what will happen is basically you have these ratios and the boxes will be formed from these ratios. Anchors will be formed. Now these anchors might not be the perfect match, alright? So it can be possible that they may need some changes. So in that case, what this regressor, it will not give out coordinates. It will give out how much of the center do we have to change. So my object center might not be here, it might be here. So this change, delta x, delta y, that we have to calculate. So the regressor will give out those values. Alright, here let me make you understand. So this is my object, right? And here you have the sliding window, suppose. So let's say the center somewhere lies here. But we know the center of this woman, if it gives out some anchor box, should be here somewhere. So this change basically, this change will be calculated here. This change will be calculated using this regression part here, which is 1x1. Okay, so this will give out delta center, delta y center, delta x center and delta y center. How much of the center do we have to shift, as well as how much of the anchor box width or height we have to change. So that will be given out here. So this is the whole thing about RPN, region proposal network. Let me go back again and explain one by one the whole thing. Okay, so region proposal network, how does it start with? You have the feature maps. These feature maps pass through a 3x3 convolution which has padding equal to 1, and this has 512 filters. Now you have this will be again divided into two parts. It will have 1x1 convolution here. Now this 1x1 convolution will basically be used as a classifier to tell me whether this is a background or not background. And at the same time, this will also give me out 1x1 here. This will give me 4 values, okay, for each k being the number of anchors. So for each anchor it will give me 4 values. These 4 values are delta x, delta y, delta width and delta height. Now I have these values. What will happen next? See, then what will happen is we will use IOU. In RCNN, the IOU is basically set to 0.7. So if your IOU, the IOU threshold is 0.7. So that means you have these anchor boxes. Now which anchor box should we use? Because this will generate a lot of anchor boxes. So what they have done is they have used a threshold here. So if the anchor box threshold is above 0.7, okay, if that IOU, the anchor box gives the IOU with the ground truth above 0.7, in that case we will use that bounding box. Okay, if it gives less than 0.3, then we will remove that from the thing. So we will remove that from a bounding box, from an anchor box. So that will not be used as a bounding box. So what basically we have done is we have so many bounding box. In these bounding box, what we will do is we will find the IOU which comes from here classifier. The IOU with ground truth bounding box. So if that IOU is above 0.7, we will keep that bounding box. If it is less than 0.3, we will remove that bounding box. Alright. So this is basically the whole thing about RPN. Now after that, what happens is we take approximately 256 such boxes. So this is basically what you get, all the bounding boxes from RPN. So this is the whole RPN thing, but there are a lot of things we will talk about. So one of the things that is, see, this is also one thing that we got from the RPN. So all these anchor boxes, they give out everything, and there are a lot of anchor boxes that are one above the other. That means they have been overlapped, and we might not require a lot of these anchor boxes, right? So in that case, but all of these will give value above 0.7. In that case, what we do is we do something known as NMS, that is non-max suppression. We'll talk about this later in the future video. I promise you we'll talk about this, but for now what you can understand as NMS is basically if there are a lot of anchor boxes or there are a lot of bounding boxes, they have very big overlap with each other, but all of them have IOU greater than the requirement IOU. So then we do something known as non-max suppression. So in that case, it uses only those anchor boxes that have the most highest overlap. Alright, so that is something. So there is also an NMS threshold which tells you how much anchor boxes to use and all, but yeah, this is the whole thing. In this whole paper, they have not referred bounding boxes as bounding boxes. What they have referred bounding boxes are as anchor boxes. Alright, and this is the first paper where instead of using bounding boxes, regressor, what they have done is they have for each sliding window, they have generated each anchor, they have generated bounding boxes of their own. Alright, so now once you have that, now you have gotten all the region proposals. Right, you have all the region proposals. Now these region proposals are then projected on the feature maps. These feature maps were what you got in the very initial first phase, right? So now even then you see you have only classified whether that particular region is background or not background. So if it is not background, it is used for as a region proposal. Now these region proposals are then projected onto the feature maps. So here you have all this. Now this is very easy. We have already talked about how this gets projected, but I did not show you a picture. So here is a very good example. Alright, so this is a very good example of how it gets projected. See, this is the actual original image. This is 688 cross 920. This is the feature map that we get, 43 cross 58. So the subsample ratio is basically 1/16. Alright, so you get the point 340 comma 450, the center of the anchor box here. So in that case, what you will do is divide it by 16 and you get the values that will be used in the anchor boxes. This is how the projection is being done. Alright, so once you have these projections, now obviously these projections are going to be of different sizes. In that case, what we will do, the next thing is ROI pooling, that is region of interest pooling. So region of interest pooling is basically max pooling, and what it does is when you have regions of different sizes, it extracts them into features so that the features are of same size. So if you remember, what happens is if you have an 8 cross region of interest and you want a feature map of 2 cross 2, what will you do is you will divide this by 2 cross 2 and you will get 4 cross 4. So now this 8 cross 8 this 8 cross 8 region proposal will be divided into 4 cross 4 boxes, and then you will get do max pooling, and you will finally get 2 cross 2 feature map that is required. Alright, so this is basically ROI pooling, and everything else remains the same. You have the ROI pooling. Now this is for moved forward by 2 fully connected layers. You have multi-class classification and bounding box regressor. Multi-class classification basically softmax. Here you will not have to use k plus 1, you will only use k, and you have then the bounding box. This just gives you the bounding box values that can be improved. So just a recap, you have the input layer. This is passed, input image is passed only once into a convolution layer. You get all the feature maps. These feature maps are passed through RPN. RPN is a region proposal network. So region proposal network is basically composed of one 3 cross 3 convolution which has 512 filters and padding of 1, and it has 2 sister siblings. One sister sibling is used as a classifier, other is used to improve the bounding box values. So each image will have each image will be passed through a 3 cross 3 sliding window. In this 3 cross 3 sliding window, center will be used as an anchor, and this anchor will be used to generate a lot of anchor boxes. Once you have these anchor boxes, what will happen next is these anchor boxes will now be passed into this. So these anchor boxes have been generated, and this feature maps will be passed into 3 cross 3 convolution, and these anchor boxes will be used for classification and regression part. So classification will basically tell whether this is a background or not, and to solve this problem what they have done is they have added an IOU, intersection of union with the ground truth. If it is greater than 0.7, then they will use that bounding box or that anchor box as as a positive that can be passed on further into the feature map that can be projected here. So approximately you get 256 such bounding box or anchor boxes. So one thing is that 2000 take a lot of time, so that is why it had to be reduced, and in faster RCNN they have reduced it to 256 anchor boxes. Once you get these anchor boxes, they are projected. We talked about how the projection works. We talked about subsampling ratio. Then they are passed through a region of interest pooling. So region of interest pooling is basically what? Region of interest pooling helps in making the feature maps of the same size. Once that is done, it will be used, passed through 2 fully connected layers, and then finally 2 sibling networks, and they will be used for classification and regression. The loss, let us talk about the loss here now. So the loss is basically log loss that you get from here, multi-class classification, and this is added with regression loss. Regression loss is basically smooth L1. Alright, so this is the whole thing, and also this loss, this will be for each anchor box, by the way. So for each anchor that has been generated, for all the 256 anchors, this will go on, and you will get then the final loss. Alright, so you have the whole thing, you got the regions, you got region of interest, and you finally did the classification. How much time did it take? It took 10 milliseconds. So from 2 seconds it went down to 10 milliseconds. Now this is a model that can be used for a self-driving car or any real-time detection. Alright, so now we have the whole thing as is. Okay, I forgot about this. So there was this other part also, we did not revise about that. Yeah, so when we will be finding out the values, they will be delta x, delta y in regression, and delta height and delta width, instead of finding the actual coordinates, because it is difficult to find the actual coordinates, hence we will be using delta values. So this is the first time that instead of using anchor boxes, these anchor boxes have been generated, right? So instead of using selective search, now we have anchor boxes that are being generated on their own, and in the future architectures you will see that these anchor boxes are generated on their own. In the future they have used this type of method to generate more bounding boxes rather than using an algorithm that generates the boxes for them. Alright, so that is it. I hope you enjoyed the video and keep learning.